If we ever want to simulate a universe, we should probably start by learning how to simulate even a single atomic nucleus. But it's taken some of the most incredible ingenuity of the past century to figure even that out. So today, I get to tell you how to simulate a very, very small universe. Physics has been insanely successful at finding the underlying rules by which the universe operates. It helps that a lot of those rules seem to be mathematical. By writing down the laws of physics as equations, we can make predictions about how the universe should behave. That lets us test our theories and basically become wizards capable of predicting the future and manipulating the foundations of reality. But our wizarding only works if we can solve the equations, and it's impossible to calculate perfectly the evolution of all but the most simple systems. That's especially true when we study the quantum world, where the information density is obscenely high. As we saw in a previous episode, it takes as many bits as there are particles in the universe to store all the information in the wave function of a single large molecule. We also talked about the hack that lets us do that anyway. It's called density functional theory. DFT is good for simulating the electrons in an atom, but the behavior of electrons is comparatively baby stuff compared to the atomic nucleus. Every proton and neutron is composed of 3 quarks stuck together by gluons. Well, actually, that's a simplification. Every nucleon is a roiling, shifting swarm of virtual quarks and gluons that just looks like 3 quarks from the outside. The messy interactions of quarks via gluons is described by quantum chromodynamics, or QCD, in the same way that quantum electrodynamics describes the interactions of electrons and any other charged particles via photons. We're going to come back to a full description of QCD very soon, but you don't need it for this video. Today, we just need to understand why it's complicated. Instead of the one type of charge in QED, in QCD there are 3, which we call color charges, hence the chromo in chromodynamics. Also, quarks never appear on their own, they're always bound to other quarks in composite particles called hadrons, of which protons and neutrons are an example. To test QED, we can chuck a photon at an electron and see what happens. But to test QCD, we can't just poke a quark with a gluon, instead we need to figure out what the theory predicts about the properties of hadrons that are actually measurable. And that's near impossible because of a third problem. The force mediated by gluons is very strong, earning it the name the strong force. And that strength turns the interior of the hadron into a maelstrom of activity which can't possibly be calculated on a blackboard, and at first glance looks impossible to simulate on any computer we could ever build. Or would be if it weren't for the fact that people are exceptionally clever and they came up with lattice simulations. Now, before we do the hard stuff, let's review the comparatively easy quantum electrodynamics. Say we want to predict what happens when 2 electrons are shot towards each other. We can actually calculate the almost exact probability of them bouncing apart at a given speed and angle. We do that by adding up all the possible ways that interaction could happen. For example, there are various ways that the first electron could emit a virtual photon which is absorbed by the second electron, or vice versa. Or it could happen via 2 virtual photons or more, or one of those photons could spontaneously form a virtual electron-positron pair before becoming a photon again, and so on. Each family of interaction types is represented by a Feynman diagram, and quantum electrodynamics gives us a recipe book for adding up the probabilities. We talked about this stuff in some previous videos, but there are literally infinite ways this interaction could happen, each more complex than the last. So, how do you know when to stop adding up your Feynman diagrams? Well, we kind of got lucky with that in the case of QED. As the interactions get more complicated, their probabilities get smaller and smaller. Diagrams with more than a few twists and turns add almost nothing to the probability, so we only have to include the simplest few levels. Each pair of vertices on a Feynman diagram represents the probability of a pair of electrons interacting with the electromagnetic field, emitting and absorbing a virtual photon. And there's a set probability of that happening each time. It's around 1 over 137. So every time you add another pair of vertices to a Feynman diagram, the interaction it represents becomes 137 times less likely. A diagram with only 6 vertices is nearly 20,000 times less likely than the simplest 2-vertex diagram. So we just choose the precision we want for our calculation and ignore any interactions that nudge the probability by less than that precision. This 1/137 thing is the fine structure constant. It's the coupling strength between the electron and the electromagnetic field. The smallness of the fine structure constant means the electromagnetic interaction is relatively weak, relative to the strong force anyway. Okay, back to the strong force. Now let's say we have 2 quarks hurtling towards each other. They're going to interact by the strong force, which is mediated via virtual gluons of the gluon field rather than virtual photons of the electromagnetic field. We can draw Feynman diagrams of these interactions, now with cute curly gluon lines. Presumably, then, to calculate the probability of a given interaction, we again just add up diagrams, with the probability of each diagram determined by the number of vertices. The coupling strength for the strong nuclear force is ingeniously named the strong coupling constant. It is much higher than the fine structure constant, and it's of order 1, although it depends on the energy scale. That's what makes the strong force strong, and it's also what makes the strong force interactions very difficult to calculate. You no longer have the luxury of throwing away all but the simplest Feynman diagrams when you're calculating the interaction probability for your pair of quarks. Adding new vertices doesn't decrease the probability anywhere near as quickly as with QED. This means you can't possibly do this calculation with pen and paper. In fact, it's extremely challenging to do QCD with the Feynman diagram approach, even with computers. Now, before any particle physicists start shouting at me, I'll quickly add the caveat that there are some unusual cases where the strong coupling constant can become small and quarks can be understood with Feynman diagrams, and this is the phenomenon known as asymptotic freedom. But if I tried to explain that too, we would be here all day. In general, if we can't calculate what quantum chromodynamics predicts for the behavior of quarks, then how can we even test the theory? Well, we need to abandon Feynman diagrams. In fact, we need to abandon the idea of particles altogether. See, it turns out that the virtual particles that we were using to calculate particle interactions don't actually exist. Now, we've talked about that fact recently. Real particles are sustained oscillations in a quantum field that have real energy and consistent properties. Virtual particles are just a handy calculation tool, a way of representing something deeper. They represent the transient disturbances in quantum fields due to the presence of real particles that couple to those fields. The coupling between quark and gluon fields is so intense that the disturbances of those fields are way too tumultuous to be easily approximated by virtual particles. Instead, we have to try to model the field more directly, and that's where lattice QCD comes in. It's an effort to model how the quantum fields themselves evolve over the course of a strong force interaction. Similar to how Feynman diagrams work, to do this you need to account for all possible paths between the starting and final field configuration to get the probability of that transition happening. Now, there's a good reason we don't do this for electromagnetism. There's an astronomical number of configurations that the field could pass through in the intervening time. No supercomputer could do that even given the entire life of the universe. For QED, Feynman diagrams let us reduce the number of field configurations by approximating them as virtual particles. But for QCD we have to stick with fields, and so we need a different hack. In fact, we need a few of them. Let's make sure we understand exactly what we're trying to do here. We want the probability that some wiggly quantum field wiggles between one state and another. Let's go back to electromagnetism just for a second because there's an analogous case here, and one that we've already covered. So before Richard Feynman came up with his famous diagrams, he devised a way to calculate quantum probabilities called the Feynman path integral. It calculates the probability that a particle will move from one location to another by adding up the probabilities of all possible paths between those points. Actually, it also includes the impossible paths, but there's no time to explain that right now. Every time you add the probability for a single Feynman diagram, you're actually adding infinite possible trajectories using Feynman path integrals. In lattice QCD, we want to do something like a Feynman path integral, but instead of trajectories through physical space, we add up trajectories through the space of field configurations. And that is much harder to do for 3 reasons. First, any patch of spacetime technically contains an infinite number of points, and no computer can hold an infinite amount of memory. So we need to pixelate spacetime so there's only a finite number of points. But even then, there's still an astronomical number of ways that the field can move from the starting to final configuration. And because these configurations are messy, we can't do a simple integration like in the Feynman path integral. So our second trick is called Monte Carlo sampling. This is an extremely common computational method in which you do your calculation based on randomized selections from some distribution. So we randomly choose a selection of field configurations of a pixelated space that get us from the start to the end of our interaction. But these can't be totally random because some of these paths are still more likely than others. In the Feynman path integral, the probability of each path comes from adding up all of the little shifts in the particle phase from each step. Then, at the end of the path, you add together the phases of all possible paths to get the total probability of reaching that point. This is exactly like the famous double-slit experiment, where the probability of a particle landing at a certain point on the screen depends on whether the phases of different paths through both slits add together or cancel out. Our quantum field is a 3D pixelated lattice that evolves through time. As with the path integral, each time step results in a complex valued phase shift at each spatial point. Those complex numbers are fine in the Feynman path integral because they get squared at the end and they disappear, but they're very difficult to deal with in Monte Carlo approaches. So you need one more hack, our most ingenious yet. We're going to pretend that time is just another dimension of space. This operation is called the Wick rotation, and it eliminates the complex nature of the phase shifts. If we then pixelate the time dimension, we have a lattice with 4 spatial dimensions. Now our coupled quark-gluon field looks like this, a lattice of points with connections. The points are the quark field and the connections are the gluon field. Getting rid of the complex quantum probabilities means that this isn't really even a quantum problem anymore. The structure just looks like a crystal, admittedly a 4-dimensional one, but a classical crystal. And guess what? We understand how crystals work extremely well. We can now simulate how this lattice evolves over time using the laws of statistical mechanics. Now, we're not all the way there yet. After all, spacetime isn't really a discrete lattice of points. But it turns out that the things you want to calculate, like the mass of a hadron, actually do depend on your choice of pixel size. But they depend on it in a very simple way. You can run your simulation multiple times for different lattice spacings to figure out that relationship. For example, the prediction for neutron mass gets larger with increasing lattice spacing. But if you just draw a straight trend line through your simulation results, you can find out the neutron mass in the case of 0 spacing, a continuous spacetime. And guess what? This gives us the correct neutron mass. This trick of transforming quantum fields into a lattice was first discovered by Ken Wilson all the way back in 1974. Back when you'd be lucky to fit a kilobyte of RAM on your computer. Since then, and with the help of vastly improved computational resources, lattice QCD has accurately predicted many things, from the masses and decay frequencies of hadrons to the exotic properties of quark-gluon plasma. These simulations were also an essential part of the prediction side of the new muon G2 results. The fact that lattice QCD even works gives us deep insights into the nature of quantum fields. For one thing, because it doesn't use virtual particles at all, but rather simulates the quantum field more directly, that helps us put to bed the idea that virtual particles are anything more than an approximation of what these messy fields are really doing during an interaction. So there is your whirlwind introduction to lattice QCD. As our computing power grows, one day we'll likely to be able to build detailed simulations of entire collections of hadrons, like the nucleus of a single atom. We will never simulate a whole universe this way, nor anyway, in all likelihood, but we're going to learn so much just by simulating these tiny patches. of spacetime. Before we get to comments, I just want to thank everyone who supports us on Patreon. It is incredibly helpful and greatly appreciated. If you would like to join us on Patreon, there is a link in the description. And no matter what level you join at, you'll get access to our hopping Discord, as well as access to every script that I've ever written. Okay, on to comments for the last 2 episodes. There's the one on superdeterminism, and the one where we talked about what a state of matter really is. iBooba points out an error in our definition of absolute zero temperature. We said that it's defined as zero kinetic energy in the particles, but actually this doesn't account for particle vibrations, which is also a place where thermal energy can live. Better to define absolute zero as all particles being in their ground quantum mechanical states. And this is important because even in these ground states, there's still some energy, ground state vibrational modes, for example. So thanks for the correction, iBooba. Elad Lerner tells us of another example of where different states of matter can appear on different hierarchical scales. And that example is plate tectonics. The Earth's upper mantle is mostly solid on scales less than around a kilometre, but on larger scales it's hot enough to flow like a liquid and move around entire tectonic plates. So in a sense it's both a solid and a liquid, a state called a plastic in the Earth science. Thanks for dropping the wisdom, Elad. Okay, moving on to superdeterminism. I would compliment you for asking so many excellent questions, but I guess you really didn't have a choice in the matter. David Dunmore proposes a non-quantum version of the EPR paradox experiment. Take a pair of gloves, put them in separate sealed boxes, and give one to a friend randomly. When you look in your box to see that it's the left glove, say, then you instantly know that your friend has the right glove. David asks whether this is a valid comparison to the entanglement experiment done with a pair of electrons with undefined but opposite spins to each other. In the case of the electrons, those states aren't simply unknown, they are undefined, or at least they're each in a superposition of being in both states, both up and down at the same time, and that means that the actual direction of the spin gets randomly chosen at the moment of measurement. Now, if the spin direction could only be up or down, then it might be impossible to tell the difference, whether the randomization happens when you put the electrons or gloves in the box, or whether it happens when you open the box. But electron spin also has a directional axis, either up, down, left, right, forward, back. And that gets defined by the choice of your experimental axis at the moment of measurement. You'll always measure a fully up or a fully down electron no matter what direction the spin was initially prepared in. Its entangled partner then has to have opposite spin, but that opposite spin is going to be along the same axis that its partner was measured in. And it's the correlation between the spins measured for one electron and the choice of the direction of the measurement axis for its entangled partner that is the subject of the Bell test and the source of all this spookiness. And yes, it seems that the spin direction really is set at the instant of measurement, unless of course our choices of measurement direction are enforced, which is what superdeterminism is saying. The Purpleberry asks whether, under superdeterminism, we could determine the spin direction of an electron without measuring it, only confirming it afterwards. Well, actually, entanglement lets us do that without even resorting to superdeterminism. Like the glove in the box analogy, if you can measure the spin of an electron's entangled partner, then you know what its spin is. However, that measurement isn't a passive act. You will have actually forced the electron spin to be in some direction based on that initial measurement. Crazy Don't Mean Wrong says that the fun thing about determinism is that it doesn't matter. Either we have free will or we don't and never did, yet we still act as though we do because what else can we do? Whether or not the universe is deterministic, there's still only one question that matters, and that is, how can I abuse the rules of reality to survive past the death of the stars and live to see the release of Half-Life 3? Well, the worst part is that in a superdeterministic universe, it's already defined that you will wait for the heat death and that it'll have been for nothing. But at least there's nothing you can do about it. So why worry?